What comes to mind when you hear the word Dune? A sand dune in the desert? A science fiction novel? When I say it the month before July, Dune, 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 Dune. To me, Dune is the Deep Underground Neutrino Experiment, an international collaboration hosted by Fermilab. Dune will explore some of the exciting aspects of neutrinos we've been talking about in this series. It's under construction now, and it is a huge endeavour. Scientifically a big deal, but also literally huge. As in 68,000 tonnes of liquid argon huge. 4 detector modules, each as long as a commercial jet huge. Plus, it's a mile underground. Dune will be by far the largest liquid argon neutrino experiment ever. So how do we go about developing such a massive detector? That's what we're talking about today on Even Bananas. Imagine you're a violinist in an orchestra and you've got a big concert coming up. How do you get ready? Do you sit around making really detailed plans on paper and then show up to the concert without ever having picked up a violin? I mean, you could, but it wouldn't go well for you. Instead, you'll spend hours practicing, trying out different things and improving your skills. You can never fully replicate the performance experience, but you do as much as you can to prepare. We physicists are in a similar situation when it comes to studying neutrinos. Dune is like the big concert we're practicing for. There's no substitute for the experience of building and running the experiment, but there's a lot we can do to make sure we're ready for it. Here's what we have to prepare ourselves for. A particle accelerator at Fermilab will generate the world's most intense beam of high-energy neutrinos. The beam will be fired in a straight line through 2 detectors. The first detector will be at Fermilab. The second detector, the 4 commercial jets one, will be at the Sanford Underground Research Facility in South Dakota. Having 2 detectors so far apart will allow us to compare the neutrinos and better understand their shape-shifting behaviour called oscillation. We talked all about how these measurements work in previous episodes, so if you haven't seen them, go back and check it out. I'll leave a link in the description. One of the really innovative things about Dune is the type of detector it will use. Liquid argon time projection chambers. I mean, a time projection chamber. Could that sound any more futuristic? To find out more about how we're preparing to build these detectors, I'm joined by Brian Ramson, a Fermilab physicist who works on Dune and Nova. Hey, Brian.
Hey, Kirsty. Hi, Internet. I'm working on an experiment called Proto-Dune, which is a prototype detector for Dune. Proto-Dune is located at CERN and is a cube about the size of a 3-story house. It's filled with about 800 tons of liquid argon.
Despite being a small testbed for the massive FAR detectors, Proto-Dune is already the biggest liquid argon detector ever built. We use it to check out all sorts of important things like the fluid dynamics of cold liquid argon, how the electronics are reacting, and even the software that will gather and analyse our neutrino events. We also get to try out advanced new technologies and figure out what will work best for Dune, like trying variations of a piece of music to work out the perfect melody.
One of the things I'm really interested in is our system for detecting light, called photon detectors. Using this, we'll be able to make better measurements of neutrinos from supernovae, which can give us a look at how stars explode and form black holes. We can also search for signals of proton decay, which have never been seen before, and some grand unified theories predict it should happen with a decay lifetime of more than 100,000 billion years. In Proto-Dune, we've tested out a mix of older and newer technologies to see which is better. A photon detector technology called Arapucas, designed by our Brazilian collaborators, did really well. It's a new idea that collects a lot of light from around the detector using something that's a bit like a bird trap for photons.
Proton decay, if it happens, is incredibly rare. But Dune's 68,000 tons of argon will have a lot of protons. So we'll be looking for it with the help of these advanced light detectors. But as well as being a test run for Dune, Proto-Dune is also making its own physics measurements.
We see neutrinos in Dune, or in any neutrino experiment really, by looking at the particles produced when they interact in our detectors. To do that accurately, we need to understand what different types of particles look like in liquid argon detectors, and whether those particles are likely to go on and also interact again with another argon atom. The easiest way to do that is to fire known types of particles into the detector and see what they look like. So that's exactly what we're doing with the particle beams at CERN.
Thanks, Brian. Proto-Dune is a huge milestone in our progress towards Dune, and it's the latest in a line of increasingly advanced liquid argon detectors at Fermilab. Fermilab's first liquid argon neutrino experiment was Argonute, which could basically fit on your dining table. Since then, we've progressed to Microboon, about the size of a school bus, and soon to be joined by SBND and Icarus, both slightly bigger. And we have Proto-Dune, the size of a large house. In addition to new information about neutrinos and the particles they produce when they interact, in each of these steps we've got better acquainted with what liquid argon can do, how different systems work together, and how we can build the best detector possible. We've got our parts down to a T, and soon we'll be ready for the big performance. Dune is going to do a lot of cool science. Watching for neutrinos from supernovae and the decay of protons is just the start. You already know that one reason neutrinos are my favourite fundamental particles is that they could be the key to why there's more matter than antimatter in the universe. That is one of Dune's big science goals, and we'll talk about it next time on Even Bananas. Fun fact! At minus 300 degrees Fahrenheit or minus 184 degrees Celsius, the inside of each Dune detector will have about the same average temperature as Saturn's atmosphere. It's so cold that each detector module will shrink by about 16 centimeters when the liquid argon is added.